Good evening, students. It's Mr. D. I have posted another set of problems on Canvas this afternoon. So there are two problems. It is Impulse-Momentum Theorem. There's a softball problem and a rocket problem. I'm going to do number one with you, the softball problem. So a 0.174 kilogram softball is pitched horizontally at 24 meters per second. The ball moves in the opposite direction at 37 meters per second after it is hit by the bat. Now on part A, it says draw arrows showing the ball's momentum before and after it hits the bat. So I've already drawn a picture of the initial situation here. We have a pitcher throwing the ball to the batter, and so initially the softball is headed in this direction, and if I set up a coordinate system here, I can say positive x direction is this way. So after the batter hits the softball, it's going to move this direction, which by our coordinate system is a positive x direction. So if I set up a before and after situation, we have the ball. The ball's velocity is headed in this direction. Now velocity is a vector, so momentum will be a vector. So we have a negative velocity because our vector arrow is pointing in the negative x direction, and we will have vector, a momentum vector, and this is going to be identified by lowercase p. This is before the bat hits the ball. So after the bat hits the ball, we have a velocity going this way. So you can look at the picture here. The bat hits the ball, so the ball is going to go in a positive x direction. That's the velocity, and we have a momentum vector right there. So for part B, it says calculate the change in momentum of the ball caused by the bat. And so what we really need to think about is the ball is moving at 24 meters per second initially. It hits the bat, and as it hits the bat, it actually comes to a stop. And then the force of the bat is going to accelerate the ball in the opposite direction that it was originally thrown, and it's going to achieve a speed of 37 meters per second. So when we calculate change in momentum, we use the equation delta P. So the Greek letter delta represents change in momentum. We have the final momentum of the softball minus the initial momentum of the softball. The final momentum of the softball is going to be mass times the final velocity of the ball minus the mass times the initial velocity of the softball. So we know all of these values, so let's go ahead and plug them into our equation. So our mass is 0.174 kilograms. We're going to multiply this by the final velocity of the ball. So our final velocity of the ball is 37 meters per second. And if we look at our diagram here, the final velocity is moving in a positive x direction. And we can also see that right here. So we are going to associate a positive sign with this velocity. So 37 meters per second minus the mass, 0.174 kilograms, multiplied by the initial velocity of the softball. So that is 24 meters per second. But if you take a look at what we set up initially, this is going to have a negative velocity, because remember, velocity is a vector and it does show direction. So this is going to be negative 24 meters per second. Okay, so go ahead and get out your calculator, and we're going to take the product of these two values, so the mass and the final velocity of the object. This is going to be 6.438. Now let's take a look at our units. I have kilograms multiplied by meters per second. So we're going to have units of kilogram meters per second. Now, we're going to subtract right here our initial momentum. So 0.174 times negative 24. This is going to give me a negative 4.176. And our units are kilogram meters per second. So I have two negatives here. So this is going to give me a positive. We have 10.614 kilogram meters per second. So our change in momentum is 10.614 kilogram meters per second. Okay? Now what we need to do is take a look at part C. If the bat and the softball are in contact for 0.85 milliseconds, what is the average force the bat exerts on the ball? So, my time interval, or my time of contact, 0.85 milliseconds. This is going to be 0.00085 seconds. And what is the average force? So what we're going to do is use the Impulse-Momentum Theorem. So our equation for impulse is the average force applied to the object multiplied by the time interval of that applied force is equal to the object's change in momentum, which is identified by delta P. So we have force is equal to, now you've already calculated the change in momentum at 10.614 kilogram meters per second. You're going to divide this by the time interval of contact, the time that the bat contacts the ball, 0.00085 seconds. So let's take a look at the numerical value first, then we'll talk about the unit value. So 10.614 divided by 0.85 milliseconds is going to give me a force of 12,487.05. Okay? So let's take a look at units here. In my numerator, I have kilogram meters per second. In my denominator, I have seconds. And algebraically, we can write this as seconds over 1. And we need to think about that old algebra rule that tells us whenever we divide fractions, it's like multiplying by the inverse of the denominator. So when I set up my units here, I have kilogram meter per second multiplied by the inverse of our denominator here. So the inverse of seconds over 1 is going to be 1 over seconds. So when we multiply our fractions, we just multiply straight across here. So in my numerator, I have kilogram meters. In my denominator, I have seconds times seconds, which is going to be seconds squared. And what is a kilogram meter per second squared? That is a Newton. So our answer, the force applied by the bat to the ball, is 12,487.05 newtons. So on your own, complete problem number 2. Take a picture of it and send it to me, and I will give you credit.